Now that we have two models built, we need to compare them to see if we're actually improving the outputs that we get from each of the models, or at least from the full model. So remember, we create the baseline model as our benchmark, as just our reference point to see if adding more variables is improving the overall predictability of the model. So on the left side, we have the baseline regression statistics. On the right side, we have the full model regression statistics. So the values that we want to focus on are the values that we highlighted. So multiple R, that's our correlation coefficient. We can see a significant increase in the multiple R from the baseline model to the full model. That's a good sign. We want to see that number go up. The other thing is the adjusted R squared. Okay, so when we compare the adjusted R squared from the baseline to the full model, we also see a very significant increase in those values. So with the baseline model, we could only explain 49.15% of the variation in sale price using the living area variable alone. When we add our other three variables, borough, fireplaces, and overall quality, we see that adjusted R squared improved to 85.67%, meaning that we can now explain 85.67% of the variation in sale price. So almost or a little more than a 35% increase in the amount of variation we can explain in sale price. Now remember, if we can explain 100% of the variation in sale price, that means we can predict it perfectly. So that is also a criteria that we can use to assess improvement. The last value that we have highlighted is standard error. Now, while you want to see multiple R increase and we want to see adjusted R squared increase, but we want to see standard error decrease, that means that we are overall decreasing the amount of error in our predicted values from what the actual values were. So we see multiple R increase, adjusted R squared increase, and standard error decrease. All good signs. We can also look at the residual plots for the living area variable, since that is the one independent variable that's consistent with each of these models. Now, when we look at our baseline model, we still see kind of an unequal variance of residuals. We see that fanning pattern, which is not what we want. But when we add more useful information into our model, we can see that the residual values are smoothing out a little bit. And we don't have that growing pattern of residuals. In fact, they're pretty fairly consistently distributed from the left to the right. Now we do have a couple errors that we need to address, but overall, all of these things that we're looking to improve have improved from the baseline to the full model. That means that it was worth adding these additional predictors, and overall, it is increasing the predictive power of our model. So I'm going to go now to assessing the full model alone. So we've just compared the baseline to the full. So we compared our full model to our benchmark model, and we see those improvements. Now let's dig a little bit deeper into the actual full model. Okay, so here is the output from the full model. Now there's a couple of the dummy variable residual plots that are missing because they basically look very similar to the Crawford dummy variable. But if you look at your plots, they should look the same. Now I've highlighted some of the problematic points in each of these plots. They're red. Okay, so if you just double click on any point in a plot and right click, then you can fill it in with a different color, and that's all I've done here. So the first thing I'm looking at is our model table. So one thing that we want to assess is that each of these independent predictors that we're putting into the model is actually adding useful information. So the way that we do that is by looking at the p-value and assessing if it's less than 0.05. So all of the p-values associated with our independent predictors are less than 0.05, which is an indication that they're adding useful information. Okay, so that's what we get from our model table. Now, when we look at our reformatted normal probability plot, we have a problem. Okay, we really want to see that line, that normal probability line, as straight as possible. Now, it's going to be really hard to get it perfectly straight in real world scenarios, but this is assessing our model assumptions of normality. So what we see here is that the tails in these normal probability in this normal probability plot are too long. It's too snaky. Okay, so and these are just houses where we were very off in our prediction. They had a really high residual value. Um, if we look at our residual plots, we can see that we'll also have some violations with this normal variability in the residual values. So remember, we kind of want to be able to draw like a rectangle over this residual plots. We don't want to see any significant patterns. We don't want to see any plots just points just floating out in space. So if we look at this living area variable, we can see residual plots. We can see these 3 red values down here to the bottom that are kind of outside of the norm. If we draw a straight line right at -10 and a straight line right at +10, we can see that those values are outside of that. And then this one really, this is kind of close, but this one up here at the top. Now we also see 4 plots, 4 points in the fireplaces in roughly the same place as far as it's where the residual value is concerned. Same thing with overall quality. Same thing with each of our dummy variables. So the good news is it's only 4 houses, only 4 data observations out of 1,521 that are the culprits for these violations. So in part 2 of our linear regression lab, we're going to learn how to remove these values from the data and rerun the model so that we're no longer violating those model assumptions. And then we're going to learn how to use this model for prediction. So, but one thing that we have to be able to assess is which of these houses are, we just really far off in our prediction. And it could be because, it's a really, really large house with really low quality. So maybe we predict it to be more money than it is, than it actually sold for. So there's something about the house features that are just not typical of what you normally see, and it's creating a large error in what we expect that value to be, which is why the residual is either very, very small or very, very large. Okay, so in lab 2, we'll talk about those, how to remove those values and then rerun the model.